In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. For instance, consider the optimization problem maximize f subject to g equals 0. We need both f and g to have continuous first partial derivatives. We introduce a new variable called a Lagrange multiplier and study the Lagrange function defined by where the lambda term may be either added or subtracted. If f is a maximum of f for the original constrained problem, then there exists lambda 0 such that is a stationary point for the Lagrange function. However, not all stationary points yield a solution of the original problem. Thus, the method of Lagrange multipliers yields a necessary condition for optimality in constrained problems. Sufficient conditions for a minimum or maximum also exist. Introduction. One of the most common problems in calculus is that of finding maxima or minima of a function, but it is often difficult to find a closed form for the function being extremized. Such difficulties often arise when one wishes to maximize or minimize a function subject to fixed outside conditions or constraints. The method of Lagrange multipliers is a powerful tool for solving this class of problems without the need to explicitly solve the conditions and use them to eliminate extra variables. Consider the two-dimensional problem introduced above. Maximize f subject to g equals 0. The method of Lagrange multipliers relies on the intuition that f cannot be increasing at a maximum in the direction of any neighboring point where g equals 0. If it were, we could walk along g equals 0 to get higher, meaning that the starting point wasn't actually the maximum. We can visualize contours of f given by f equals d for various values of d, and the contour of g given by g equals 0. Suppose we walk along the contour line with g equals 0. We are interested in finding points where f does not change as we walk, since these points might be maxima. There are two ways this could happen. First, we could be following a contour line of f, since by definition f does not change as we walk along its contour lines. This would mean that the contour lines of f and g are parallel here. The second possibility is that we have reached a level part of f, meaning that f does not change in any direction. To check the first possibility, notice that since the gradient of a function is perpendicular to the contour lines, the contour lines of f and g are parallel if and only if the gradients of f and g are parallel. Thus we want points where g equals 0 and for some lambda where are the respective gradients. The constant lambda is required because although the two gradient vectors are parallel, the magnitudes of the gradient vectors are generally not equal. This constant is called the Lagrange multiplier. Notice that this method also solves the second possibility. If f is level, then its gradient is 0, and setting lambda equals 0 is a solution regardless of g. To incorporate these conditions into one equation, we introduce an auxiliary function and solve. This is the method of Lagrange multipliers. Note that implies g equals 0. The constrained extrema of f are critical points of the Lagrangian, but they are not necessarily local extrema of. One may reformulate the Lagrangian as a Hamiltonian, in which case the solutions are local minima for the Hamiltonian. This is done in optimal control theory, in the form of Pontryagin's minimum principle. The fact that solutions of the Lagrangian are not necessarily extrema also poses difficulties for numerical optimization. This can be addressed by computing the magnitude of the gradient, as the zeros of the magnitude are necessarily local minima, as illustrated in the numerical optimization example. Handling multiple constraints. The method of Lagrange multipliers can also accommodate multiple constraints. To see how this is done, we need to re-examine the problem in a slightly different manner because the concept of crossing, discussed above, becomes rapidly unclear when we consider the types of constraints that are created when we have more than one constraint acting together. As an example, consider a paraboloid with a constraint that is a single point. Yet, it is obviously a maximum and a minimum because there is only one point on a paraboloid that meets the constraint. While this example seems a bit odd, it is easy to understand and is representative of the sort of effective constraint that appears quite often when we deal with multiple constraints intersecting. Thus, we take a slightly different approach below to explain and derive the Lagrange multipliers method with any number of constraints. Throughout this section, the independent variables will be denoted by x1, x2, xn, and as a group, we will denote them as p equals. Also, the function being analyzed will be denoted by f and the constraints will be represented by the equations g1 equals g2 equals gm equals 0. The basic idea remains essentially the same. If we consider only the points that satisfy the constraints, then a point is a stationary point of f if and only if the constraints at that point do not allow movement in a direction where f changes value. Once we have located the stationary points, we need to do further tests to see if we have found a minimum, a maximum, or just a stationary point that is neither. We start by considering the level set of effort. Let the set of vectors, VL, contain the directions in which we can move and still remain in the same level set, the directions where the value of f does not change. For every vector v in VL, the following relation must hold, where the notation vxk above means the xk component of the vector v. The equation above can be rewritten in a more compact geometric form that helps our intuition, which is the same as writing this makes it clear that if we are at P, then all directions from this point that do not change the value of f must be perpendicular to f. Now let us consider the effect of the constraints. Each constraint limits the directions that we can move from a particular point and still satisfy the constraint. We can use the same procedure to look for the set of vectors VC containing the directions in which we can move and still satisfy the constraint. As above, for every vector v in VC, the following relation must hold. From this, we see that at point P, all directions from this point that will still satisfy this constraint must be perpendicular to G. Now we are ready to refine our idea further and completed the method. A point on F is a constrained stationary point if and only if the direction that changes F violates at least one of the constraints, i.e., has no component in the legal space perpendicular to G. Mathematically, this means that the gradient of f at this constrained stationary point is perpendicular to the space spanned by the set of vectors Vc, which in turn is perpendicular to the gradients of the constraints G. Single constraint revisited for a single constraint. We use the statement above to say that at stationary points the direction that changes f is in the same direction that violates the constraint. To determine if two vectors are in the same direction, we note that if two vectors start from the same point and are in the same direction, then one vector can always reach the other by changing its length or flipping to point the opposite way along the same direction line. In this way, we can succinctly state that two vectors point in the same direction if and only if one of them can be multiplied by some real number such that they become equal to the other. So, for our purposes, we require that if we now add another simultaneous equation to guarantee that we only perform this test when we are at a point that satisfies the constraint, we end up with two simultaneous equations that, when solved, identify all constrained stationary points. Note that the above is a succinct way of writing the equations. Fully expanded, there are n+1 simultaneous equations that need to be solved for the n+1 variables which are lambda and x1, x2, xn. Multiple constraints for more than one constraint. Similar reasoning applies. Each constraint function has a space of allowable directions the space of vectors perpendicular to the set of directions that are allowed by all constraints is thus the space of directions perpendicular to all of the constraint gradients. Denote this space of allowable moves by and denote the span of the constraint gradients by. By the discussion above, the space of vectors perpendicular to every element if is an optimum, then any element not perpendicular to is not an allowable direction. One can show that this implies. Thus there are scalars lambda1, lambda2, lambda_m such that as before. We now add simultaneous equation to guarantee that we only perform this test when we are at a point that satisfies every constraint. We end up with simultaneous equations that, when solved, identify all constrained stationary points. The method is complete now, but as mathematicians delight in doing, these equations can be further condensed into an even more elegant and succinct form. Lagrange must have cleverly noticed that the equations above look like partial derivatives of some larger scalar function that takes all the x1, x2, xn and all the lambda1, lambda2, lambda_m as inputs. Next, he might then have noticed that setting every equation equal to 0 is exactly what one would have to do to solve for the unconstrained stationary points of that larger function. Finally, he showed that a larger function with partial derivatives that are exactly the ones we require can be constructed very simply as below. Solving the equation above for its unconstrained stationary points generates exactly the same stationary points as solving for the constrained stationary points of f under the constraints g1, g2, gm. In Lagrange's honor, the function above is called a Lagrangian. The scalars lambda1, lambda2, lambda_m are called Lagrange multipliers, and this optimization method itself is called the method of Lagrange multipliers. The method of Lagrange multipliers is generalized by the Karush-Kuhn-Tucker conditions, which can also take into account inequality constraints of the form HC. Modern formulation via differentiable manifolds. Finding local maxima of a function whereas an open subset of is done by finding all points such that then checking whether all the eigenvalues of the Hessian are negative. Setting is a nonlinear problem and in general arbitrarily difficult. After finding the critical points, checking the eigenvalues is a linear problem and thus easy. When is a smooth function such that for all in the level set of then becomes a dimensional smooth manifold, by the level set theorem. Finding local maxima is by definition a local problem, so it can be done on local charts if, after finding a diffeomorphism from an open subset of onto an open subset, we can apply the algorithm in the previous paragraph to the function. While the above idea sounds good, it is difficult to compute in practice. The entire method of Lagrange multipliers reduces to the idea of skipping that step and finding the zeros of directly. It follows from the construction in the level set theorem that is the inclusion map. Therefore, if and only if writing for by the first isomorphism theorem, this is true if and only if there exists a linear map such that, as a linear map, we must have that for a fixed. So finding a critical point of is equivalent to solving the system of equations in the variables n. This is in general a nonlinear system of equations and unknowns. In the case of several constraints, we work with and replace the condition for all with the requirement that be surjective at all such points. In this case will be a linear map, i.e. a row vector with entries. Interpretation of the Lagrange multipliers. Often the Lagrange multipliers have an interpretation as some quantity of interest. For example, if the Lagrangian expression is then so, lambda k is the rate of change of the quantity being optimized as a function of the constraint variable. As examples, in Lagrangian mechanics the equations of motion are derived by finding stationary points of the action, the time integral of the difference between kinetic and potential energy. Thus, the force on a particle due to a scalar potential, F equals minus v, can be interpreted as a Lagrange multiplier determining the change in action following a variation in the particle's constrained trajectory. In control theory this is formulated instead as costate equations. Moreover, By the envelope theorem, the optimal value of a Lagrange multiplier has an interpretation as the marginal effect of the corresponding constraint constant upon the optimal attainable value of the original objective function. If we denote values at the optimum with an asterisk, then it can be shown that, for example, in economics the optimal profit to a player is calculated subject to a constrained space of actions, where a Lagrange multiplier is the change in the optimal value of the objective function due to the relaxation of a given constraint. In such a context, lambda * is the marginal cost of the constraint, and is referred to as the shadow price. Sufficient conditions. Sufficient conditions for a constrained local maximum or minimum can be stated in terms of a sequence of principal minors of the bordered Hessian matrix of second derivatives of the Lagrangian expression.